It's hard to miss all the talk about these massive language models powering the latest AI. But if you dig a little deeper, you start to hit this fundamental question.
Yeah.
How do we actually make these things bigger and better without needing, like, a supercomputer the size of a house
Hmm.
and a utility bill? Well, you get the idea.
That is the million-dollar question, isn't it? Generally, packing more and more parameters into a model leads to better performance, sure, but the sheer computational power required, it just explodes very quickly, creates a real barrier to progress.
Exactly, and that's where this clever idea called mixture of experts, or MoE, comes into the picture.
Oh.
It's almost like assembling this huge brain trust, right?
Yeah,
But only calling on the specific experts you need for the task at hand.
right. Not having everyone work on everything all the time.
Yeah.
That's a really insightful way to put it. The MoE approach lets us build models with a vast number of parameters, representing, huge potential for knowledge and skill. But for any single piece of information you feed into it, only a small fraction of those parameters are actively engaged. This offers a promising route to significantly scale up model capabilities while keeping the computational demands, well, manageable.
Okay, let's really get into the weeds here then. We've got this fascinating paper you brought, DeepSeekMoE, towards ultimate expert specialization in mixture of experts language models. Just the title suggests they're really trying to push the limits of what MoE can achieve. What's the core idea driving their work?
What's truly captivating about DeepSeekMoE is their intense focus on reaching what they term ultimate expert specialization. Now, while traditional MoE architectures offer the concept of specialized experts, they often fall short of realizing that full potential.
Right.
The DeepSeekMoE research argues that if we can make each expert within the model learn highly specific and crucially non-overlapping types of knowledge, we could unlock a new level of efficiency and performance that we haven't really seen before.
So if I understand correctly, the goal of this deep dive is to figure out precisely how DeepSeekMoE manages to get this laser-like focus from its experts. And what the researchers found are the real-world advantages in terms of how well and how efficiently these massive models can operate. And just to be clear, all of this is coming straight from the findings detailed in the DeepSeekMoE research paper itself.
Precisely. And to understand how DeepSeekMoE makes its advancements, it's probably helpful to first look at the limitations the paper identifies in, well, conventional MoE designs.
All right, so in a standard transformer model, which is the architecture, these big language models are generally based on, you've got these layers, and within those layers are feed-forward networks, or FFNs. How are MoE layers typically integrated into this structure?
So in a typical MoE model, some of those standard FFN layers are replaced with MoE layers. Instead of just one FFN, an MoE layer contains multiple experts, and as you mentioned, each expert is essentially a smaller FFN. Then, for every piece of text, every token that comes in, a routing mechanism decides which of these specialized experts will be responsible for processing it.
Okay, so instead of one big general-purpose processing unit in that layer, you've got a team of smaller, more specialized units. They get activated depending on the kind of information being processed. But the paper points out some issues with this more traditional setup, specifically mentioning knowledge hybridity. What exactly does that mean here?
Yeah, knowledge hybridity. It refers to the problem that arises when you have a limited number of experts, and they're asked to deal with a really broad range of different types of knowledge. Think of it like having, a small number of highly specialized doctors in a huge hospital. Each doctor would need to have at least a basic understanding of many different conditions, right? Which would make it challenging for them to become truly exceptional in their own specific area.
Right, they get spread too thin.
Exactly. So similarly, in traditional MoE, an expert might be activated for different pieces of text that require very different kinds of knowledge. This makes it difficult for that expert to really leverage its specific parameters effectively for all of them.
That makes a lot of sense. So these experts end up being somewhat generalists, despite the name, which kind of dilutes their potential specialization. And the paper also discusses knowledge redundancy. What's the trouble there?
Knowledge redundancy happens when different experts within the MoE model end up learning the same common general knowledge. To go back to our hospital analogy, if every single specialist also spends a significant amount of time learning basic first aid, that's a redundant use of their valuable specialized expertise.
Definitely wasted effort.
And in MoE, if multiple experts are learning the same fundamental patterns or facts present in the training data, it's just an inefficient use of the model's capacity. Those parameters could have been much better used to learn more distinct and specialized information.
So these two issues, knowledge hybridity and redundancy, are really hindering the full potential of expert specialization that MOE architectures initially promised. It sounds like DeepSeekMoE is specifically engineered to directly tackle these limitations.
Exactly. The paper introduces two primary strategies that are central to the DeepSeekMoE architecture, and both are directly aimed at fostering this ultimate expert specialization we've been talking about.
All right, I'm eager to hear about these. The first one is fine-grained expert segmentation. What exactly does that involve?
Okay, so with fine-grained expert segmentation, DeepSeekMoE essentially takes the experts and breaks them down into a larger number of smaller, more granular units. They achieve this by reducing what's called the intermediate hidden dimension within each of these smaller expert FFNs. Now, the really important thing here is that the total number of expert parameters in the entire model and the overall computational cost, they stay the same.
Okay, so it's like taking a few larger, more broadly skilled specialist teams and reorganizing them into many more smaller, highly focused teams. But you still have the same total number of people and the same overall budget. What's the big advantage of doing that?
The key benefit lies in the vastly increased flexibility in terms of which experts can be activated for any given piece of text. Because you now have a much larger pool of these smaller, more specialized experts, you also activate more of them for each incoming token.
Ah, okay.
The paper provides a really striking example. A traditional top-2 routing mechanism with, say, 16 experts offers only 120 possible combinations of activated experts.
Right.
But if you split those into 64 smaller experts and activate 8 of them per token, you end up with over 4 quadrillion potential combinations.
Wow, that's an absolutely enormous jump in flexibility. So instead of a piece of text being processed by just a couple of relatively general experts, it can now be processed by a larger number of much more precisely tuned specialists. This sounds like it could be a game changer for that precise knowledge acquisition they're aiming for.
Precisely. It allows the diverse knowledge in the training data to be broken down in a much more granular way and learned more specifically by different experts. Each one retains a higher degree of specialization. This increased combinatorial flexibility also means the model can be far more targeted in the specific knowledge it brings to bear on a particular input.
That's a really ingenious idea. What's the second core strategy that DeepSeekMo implements?
The second key strategy is known as shared expert isolation. In this approach, DeepSeekMoE designates a specific number of experts within the model whose sole purpose is to learn and retain common knowledge, the kind of fundamental information that might be relevant across a wide range of different contexts and tasks.
So going back to our hospital analogy again, this would be like having a dedicated team focused only on those essential first aid skills and general medical knowledge that almost every patient might need, regardless of their specific condition.
Exactly.
How does having these shared experts help with the hybridity and redundancy issues we talked about?
Well, by having these isolated shared experts specifically handle the common knowledge, the other routed experts, the ones activated dynamically based on the input, they don't need to spend their limited capacity learning these generalities.
Got it.
This directly reduces the knowledge redundancy among the routed experts, allowing them to focus much more intently on acquiring and refining more specialized knowledge.
And the paper makes a point that every single token of input text is always processed by these shared experts, right?
That's correct. You can think of it as a baseline level of common sense knowledge processing that consistently happens for every piece of information the model sees. And importantly, to ensure the overall computational cost doesn't balloon, when you have these always active shared experts, the number of other routed experts that are activated for each token is actually reduced.
So it's a clever trade-off. You dedicate some computational resources to handling the foundational, common stuff, which in turn allows the other experts to become even more highly specialized without increasing the total computational load. The paper also briefly mentions some earlier research that touched on this idea.
Yes, they acknowledge earlier work as providing sort of a conceptual basis for shared experts. However, the DeepSeekMoE paper emphasizes that their approach is fundamentally rooted in an algorithmic perspective, focusing on the core benefit of reducing redundancy to enhance specialization. The earlier work might have been more driven by, say, engineering optimization considerations.
Okay, so we've got these two central strategies, breaking down experts into finer units and having dedicated experts for general knowledge. But MOE models have another potential challenge, right? The issue of load imbalance.
Absolutely. Loading balance is a critical concern in MOE. It describes a situation where some experts might get used far more frequently than others, while some might barely get activated at all. This can lead to a couple of significant problems. Firstly, it can cause something called routing collapse, where the model basically learns to rely heavily on only a small subset of its experts, which completely defeats the purpose of having this large, diverse pool.
Hmm.
And secondly, if these experts are distributed across multiple computing devices, which is often the case for very large models, an imbalance in their usage can create severe computational bottlenecks. Some devices get overloaded while others sit idle.
So how does DeepSeekMoE address this potential for imbalance? What do they do?
They introduced two specific types of loss functions into their training process to actively combat this. The first is the expert level balance loss. Its main goal is to mitigate the risk of routing collapse.
Like,
It does this by encouraging a more even distribution of the incoming tokens across all of the available routed experts. Essentially, it penalizes the model if it starts to disproportionately favor certain experts over others, like making sure you're spreading the workload fairly among your team.
that makes perfect sense. You want all your specialists to get enough practice, basically. And the second one is the device-level balance loss. When does that become important?
The device-level balance loss becomes particularly important when the experts of the MOE model are distributed across multiple GPUs or other parallel computing devices. Its primary aim isn't necessarily to ensure every single expert is used exactly the same amount, but rather to ensure that the overall computational load is balanced reasonably well across all of those devices.
Ah, for efficiency.
Yes, exactly. This is crucial for efficient training, especially with these huge models needing significant parallel processing. By preventing some devices from becoming overwhelmed while others are underutilized, you can significantly speed up the training process. The paper mentions they use a slightly smaller weight for the expert level balance loss to avoid, overly restricting the learning, while they use a larger weight for the device level loss to prioritize efficient parallel computation.
All right, so DeepSeekMoE has these innovative architectural components and these balancing mechanisms. But ultimately, the real test is how well it performs, right? What kind of validation experiments did the researchers conduct, and what were the key performance results they saw with their 2 billion parameter model?
Yeah, they carried out a really comprehensive set of evaluations across a wide range of standard benchmarks covering various language tasks. For their 2 billion parameter DeepSeekMoE model, they used a configuration with 9 transformer layers, a hidden dimension of 1280, 10 attention heads, and their expert setup was 1 shared expert and 63 routed experts. Each individual expert was about a quarter of the size of a standard FFN in a dense model of comparable size.
And how did this 2 billion parameter DeepSeekMoE model stack up against other similar size models? What did Table 1 show?
The results, yeah, in Table 1, they're quite impressive. The DeepSeekMoE 2B model significantly outperformed G-Shard 2B, which is a well-regarded traditional MOE architecture. What's even more striking is that it actually matched the performance of G-Shard 2.9B.
The 2.9 billion one.
Yes, a model that had roughly 1.5 times more expert parameters and required about 1.5 times more computation during inference.
Wow, that's a pretty substantial gain in efficiency right there. But the paper also mentioned something even more significant about DeepSeekMoE approaching the performance of its dense counterpart.
Yeah.
A model with no MOE layers, just the same total parameters.
Yes, this is a really key takeaway. The DeepSeekMoE 2B model nearly achieved the performance levels of a dense transformer model that had the exact same total number of parameters, around 2 billion.
Okay.
The researchers argue that this result strongly suggests that DeepSeekMoE is getting very close to the theoretical upper limit of performance that can be achieved by any MOE model at this scale in terms of effectively utilizing its capacity. Basically, they're making their parameters work incredibly efficiently.
So what you're saying is that DeepSeekMoE isn't just a little better, it's fundamentally changing the cost-performance equation for these large models, potentially allowing researchers with fewer resources to get state-of-the-art results.
That's a powerful implication, yes. It seems to really optimize the trade-off.
That's a really strong indicator of their architecture's effectiveness. And they didn't just rely on these headline numbers, did they? They also did ablation studies to figure out which parts were contributing most.
Exactly. Figure 3 in the paper presents those ablation studies. They systematically investigated the impact of both their fine-grained expert segmentation and their shared expert isolation strategy. The findings clearly validated that both components contribute significantly to the overall performance. Notably, they found that as they refined the granularity of the expert segmentation, making the experts even smaller and more numerous, the model's performance consistently improved. They also confirmed that having the shared expert isolation mechanism led to better performance compared to the baseline G-shard architecture. It highlights its importance.
And what did they discover about the ideal balance or ratio between these always active shared experts and the dynamically routed ones? Was there a sweet spot?
Through their experiments, they explored different ratios. They found that, for their 2B setup, a configuration with one shared expert and activating 3 out of the 63 routed experts per token yielded slightly better results compared to other configurations they tested. This finding then informed their design choices when they scaled up.
The paper also goes into some detail analyzing the degree of expert specialization DeepSeekMoE actually achieves. What were the most important findings there?
This is where it gets really interesting in understanding why it seems so effective. Firstly, they looked at the redundancy among the routed experts. Figure 4 demonstrates that DeepSeekMoE was significantly more sensitive to disabling its top routed experts compared to the larger G-shard model, the 2.9B version.
More sensitive meaning.
Meaning performance dropped more sharply when you took away one of the top experts. This sensitivity indicates that the routed experts in DeepSeekMoE exhibit lower redundancy. Each individual expert is contributing more unique knowledge and is less easily replaced by another expert in the pool.
So each of those finely segmented experts is really pulling its own weight, contributing something distinct. What did their analysis reveal about the role of the shared experts then? Were they crucial?
Their analysis strongly suggested that the shared experts are indeed absolutely critical. When they did an experiment disabling the shared expert and, to keep compute cost constant, activating an additional routed expert instead, they observed a significant drop in overall performance. This strongly implies that the shared experts are capturing fundamental general knowledge that isn't being learned by the routed experts, making them essentially irreplaceable for the model's overall understanding.
That really reinforces the idea that offloading common knowledge frees up the routed experts to focus on their specialties. What else did they find about how DeepSeekMoE acquires and utilizes knowledge?
Well, they investigated whether DeepSeekMoE could achieve strong performance even when activating a smaller number of routed experts per input. If it could, that would suggest it's more efficiently acquiring the necessary knowledge with fewer specialist consultations, so to speak.
Makes sense.
As shown in Figure 5, DeepSeekMoE was able to achieve comparable performance to G-shard even when using only 4 routed experts per token. Whereas G-shard, by its default design, always activates 2. This implies DeepSeekMoE can effectively access the knowledge it needs with a smaller, more precisely targeted set of experts.
That sounds like a hallmark of really efficient knowledge use within the model. And they even trained a model from scratch using fewer activated experts, didn't they?
Yes, in Figure 6, they compared a DeepSeekMoE model trained with only half the number of activated routed experts as G-shard, so 1 shared, 3 routed, and found that it still outperformed G-shard in several key areas.
Even with fewer active experts during training.
Yes. This result further underscores the remarkable parameter efficiency of the architecture. It suggests a much higher proportion of the parameters within the activated experts are actually contributing meaningfully, rather than being diluted by learning redundant or overly broad stuff.
So the results from the 2B experiments paint a pretty compelling picture. But what happens when you scale this approach up? The paper details scaling to a 16 billion parameter model. How did that go?
Scaling to 16 billion parameters involved increasing the number of transformer layers to 28 and the hidden dimension to 2048. In this larger configuration, they used 2 shared experts and 64 routed experts. Each token was routed to both shared experts and to 6 out of the 64 routed experts. This substantial model was then trained on a massive data set, 2 trillion tokens.
2 trillion. Okay. And how did the 16 billion parameter DeepSeekMoE perform compared to other state-of-the-art models at a similar scale?
The results are quite compelling. Table 3 presents a direct comparison with their own DeepSeek 7B dense model, which was trained on the exact same 2 trillion tokens. The 16B DeepSeekMoE achieved comparable performance to the 7B dense model.
Comparable to a dense 7B.
Yes, but with only about 40% of the computational cost required for that dense model. It showed particular strengths in general language modeling and knowledge-intensive tasks.
That's a huge reduction in compute for essentially the same performance level.
Yeah.
What about comparisons with other popular open source models like LAM-A27?
Table 4 provides that comparison.
Yep.
Once again, the DeepSeekMoE 16B model outperformed Llama 27B across the majority of benchmarks they evaluated. And again, it achieved this superior performance while requiring only about 40% of the computational resources needed for Llama 27B.
Wow.
DeepSeekMoE showed particular advantages in areas like mathematical reasoning, code generation, and its performance on Chinese language benchmarks, likely reflecting its training data composition.
And it seems like the results on the Open LLM leaderboard, shown in Figure 1, generally back this up.
Absolutely. On the OpenLLM leaderboard, DeepSeekMoE 16B consistently achieved higher rankings and outperformed other open source models with a similar number of activated parameters during inference. It even managed to match the performance of LAM-A27B, which has roughly 2.5 times the number of activated parameters. It further highlights the efficiency.
This all sounds incredibly promising for practical deployment. The paper even mentioned something quite remarkable about running this 16B model on a single available GPU.
Yes, that's a key point. Due to its efficient design, only activating a fraction of parameters per input, the DeepSeekMoE 16B model can be deployed and run on a single NVIDIA GPU with 40 GB of memory.
Just 40 gigs for a 16B parameter model.
Exactly. This is a truly significant practical advantage. It greatly reduces hardware requirements and makes these powerful models much more accessible to a wider range of researchers, developers, maybe even end users. This could really accelerate innovation.
Beyond the base model, they also explored fine-tuning it for chat applications, didn't they?
That's right. They performed supervised fine-tuning on the 16B base model using a curated dataset of conversations to create a chat version. Table 5 compares this DeepSeekMoE Chat 16B with fine-tuned versions of Llama 270 and their own DeepSeek Chat 7B.
And the results?
The results showed DeepSeekMoE Chat 16B achieved comparable, and in many cases better, performance on most conversational benchmarks, again requiring significantly less compute than the others. It continued to show strong performance in code generation and Chinese tasks within the chat setting too.
So the inherent benefits seem to translate effectively into these specialized chat models as well. And the paper even gives a glimpse into ongoing work at even larger scales.
Indeed. The final section discusses preliminary efforts scaling DeepSeekMoE to a massive 145 billion parameters. While it's still in progress, the initial results in Table 6 are very encouraging. They show substantial performance advantages over G-Shard at a similar scale, and remarkably comparable performance to their own DeepSeek 67B dense model.
Comparable to 67B dense.
Yes, but with only around 28.5% of the computational costs, and potentially even lower, down to 18.2%, with some architectural variations. They also mention plans to publicly release this 145B model once training is complete.
That's an incredibly exciting look at the future potential here. So as we start to wrap up this deep dive, what would you say are the most crucial takeaways from exploring DeepSeekMoE?
Well, I think the core takeaway is that DeepSeekMoE's innovative architecture, that combination of fine-grained expert segmentation and shared expert isolation, really represents a significant step forward. It helps realize the full potential of mixture of experts by fostering truly specialized experts. This leads to demonstrably improved parameter efficiency and overall performance compared to traditional MoE approaches like G-Shard.
And this isn't just theoretical. They've provided compelling empirical evidence across different scales, 2B, 16B, and preliminary 145B results, clearly showing these advantages in real-world performance.
Exactly. That consistent theme of outperforming or matching others while requiring a fraction of the compute cost is the major highlight. This efficiency has significant practical implications like deploying a 16B model on a single GPU. It makes this level of AI power far more accessible.
It really does feel like this could be a significant development in making these incredibly powerful models more scalable, efficient, and ultimately accessible. What are some of the lingering questions or broader thoughts this research sparks for you looking ahead?
Oh, several fascinating questions. How far can we push the fine-grained segmentation? Could these techniques be adapted to other neural network architectures beyond transformers? And perhaps most importantly, what entirely new applications and capabilities might be unlocked by having access to extremely powerful yet remarkably computationally efficient large language models?
Those are some really thought-provoking questions. And it's fantastic that the DeepSeekMoE 16B model is being made publicly available. That should really encourage further exploration and research in this very promising direction. Thanks so much for taking this deep dive with me today.
My pleasure. It's a truly exciting development in the field, definitely one to watch.